All right, thank you. A lot of good talks today. So a lot of good talks about breaking things, a lot of good talks about doing other things with security. We wanted to balance that up a little bit and talk about the other side of the fence, which is incident response. So I'm here with Aaron, and we do incident response and some forensics at Google. And we want to talk about how we are trying to scale our forensic processing and analysis a little bit. So we write some code. Aaron writes code for Turbinia. We're going to talk about that. I write some code for TimeSketch, which I will talk about in a couple of slides. And I will hand it over to Aaron to start off. Right. No, I don't. So this is actually the thing we're going to talk about today. So imagine this. Imagine that you need to create timelines because in forensics we want to figure out what hackers did. We need to figure out what happens on the systems. So imagine if you need to create 50 timelines for 50 machines, and they ask for you to be done tomorrow, right? And preferably you have done all the analysis as well, so you know what they did, and the clock is kind of ticking. So how do you handle that? And this is what we're going to try to tackle today. Aaron.
Hi, everybody. So I'm going to talk today about a tool that we wrote called Turbinia. This is one of the first tools that we'll use to help scale up our incident response efforts. Some of the goals that we had for Turbinia is, first of all, just to automate a lot of the common processes that we do every single time for every single case that we work on. Being able to automate things like Plaso, extracting strings, grepping for keywords, and those kinds of things. And then once we have that automated, that will allow us to scale this up to larger events involving more and more machines. And then another goal we had for this is being able to run all of this in the cloud. And not just because the cloud gives us some nice scaling properties, that allows us to scale up and down the workers that we have for processing things, but we also want to be able to do forensics on the cloud, meaning cloud disks and things like that. As we move more and more of our infrastructure to the cloud, we need to do more incident response for things in the cloud. A few other details about this. It's open source, written in Python. Johan and Corey wrote the initial proof of concept a couple, I guess, like 2 or 3 years ago now. We started rewriting this about 18 months ago, something like that. And it says we're good at logos here. We're actually not that good at logos. Here's one of the ones we had commissioned that we affectionately refer to as the flying ham. I think it's supposed to be a fingerprint wrapped around a turbine, but looks more like a flying ham. So we can install Turbinia to lots of different places. We have the cloud is kind of the primary thing that we're shooting for here. That allows us, again, to scale things up and down fairly easily. It also allows us to not have to run all of the infrastructure for things. We're using cloud services. But sometimes it's hard to, if we have events that happen outside of the cloud, it's difficult to ingest all of that data, large disk images and things like that. Can take a lot of time just for uploads. So we also want to be able to run this in some form locally. So we have a hybrid version that we can run with just the workers locally. Then it's just the metadata that's on the cloud, and everything stays locally with some type of shared storage. And then recently we added a mode that's fully local, so everything runs outside of the cloud with a different set of backends, and that was contributed by Facebook, Eric at Facebook. Here's kind of the overall architecture. We have clients can make requests to Turbinia just by sending pub/sub messages. And then you see the workers there in the lower left, and that can be an arbitrarily large set of workers. So in the scenario we're talking about today, it would be fairly easy just to spin up as many workers as we have machines that we want to analyze. And when Turbinia creates tasks, it also sends those task messages over pub/sub, and then the tasks pick up the data from some type of shared storage, in this case usually GCS, cloud storage. All of the state is stored in data store, and then the clients can read that out of there with cloud functions. This is the hybrid version, looks basically the same, except for the workers are outside of the cloud. And then we need some other type of shared storage for that evidence to go. Local, again, is very similar, except for we're replacing some of the components. We have Kombu for the messaging, Celery for the task queuing, and then all this data is stored in Redis. So evidence that we process can kind of be anything that we want to process. I think we have something like 10 types of evidence today. Disks and Plaso files and strings files, things like that. The definitions are in Python, and when we make requests to the server, it's really just this metadata about the evidence, and then that the actual bytes for that are held in some type of shared storage. We have these pre and post processors that run on the workers to make that evidence available on the task. We can run these pre-processors to do things like attach the disks, mount the disks. Potentially in the future, we're working on doing automatic decryption. And these things can kind of be stacked up. So for example, we have one evidence type called Google Cloud Disk Raw Embedded. And what that is just a persistent disk that has its own file system, a cloud persistent disk. And within that file system are other raw images. And that's one way that we can import images into the cloud. So a typical workflow here is the client sends a request to the server. The server looks to see what kind of evidence that is and what kind of jobs it has that knows how to process those different evidence types. It creates tasks from that get scheduled. The tasks come up, and if it doesn't already have access to that evidence, if it's a copyable evidence type, there's an output manager that will copy that evidence to the local worker, runs any of the preprocessors like we had talked about, and then it does the actual processing, running those Plaso and things like that. And as part of that, it can also generate new pieces of evidence that it feeds back to the server, and then that kind of creates a tree of these tasks and evidence pieces. So one piece of evidence can turn into lots of different things as it gets processed. And then after that, it kind of does the same thing in reverse. If you have evidence that needs to be copied off, it'll do that, and then like detach disks, unmount them, and things like that. So this is kind of that job graph that I was mentioning to you. These are some of the different evidence types and processors that we have. So you make a request to Turbinia to process, say, a cloud disk, and then that will generate these different strings and Plaso jobs and all these different things that get run in parallel on different workers. And yeah. So that's Turbinia, and I'm going to turn it back to Johan to talk a little bit about TimeSketch, which is
yes.
I'll let you talk about that.
So that's a big and complicated and complex system in 3 minutes or 5 minutes.
Yeah.
So it's a lot to take in, but that's great, right? So we had these 50 images that we needed, or 50 boxes that we needed to analyze and process. So we can use this system to do that. So if you just go back to the other slide, so all of that we can do in parallel. So say that we spin up like 30 workers, right, for this job. So we can do this overnight, and we get results by the morning. So our analysts can go in and work on it. So you can go to the one, and we all been here, right? So people working with forensics, we know that strings and greps are pretty good. They're pretty awesome tools. We like sed, we like grep, we like awk, and they're good, right? They're good in their own sense. In single cases, small scale, it's great, right? You have a CSV file with the timeline of events, and you can grep if you know what you're looking for, right? But if you want to do more exploration, and if you want to do more collaborative work, you want something else, right? So we want this. We want search. We like to search for things, especially when we are exploring, and we want to be able to filter, right? So next one. So we did that. We started taking the data that we got from Turbinia when we did the processing with Plazo that outputs a lot of events, right? So for a normal system, Windows system, you can get 4, 5, 6 million events per system, and take that times 50, and it's a lot of events, and we need to be able to analyze that. So we are putting this in a full-text search engine, index all the data, and then we built a system on top of that that we call TimeSketch. So TimeSketch is basically a very focused, forensic-focused UI on top of this full-text search. And we can use it to do collaborative things like saved searches. If you're using Splunk, you maybe are familiar with that. We can annotate the events. We can share this. We can have many of our investigators working on the same case. And this is just what we need. If we need to track lateral movements between systems, for example, in this case, we can do that in TimeSketch. You see that it's more or less like a Christmas tree, which is intentional because the different colors, there are different timelines in different systems, and you can start doing interesting things. And when we have the data indexed in a system like this, we can take that and, next slide, and visualize this in different ways. You see here's a brute force attack on a Windows system. You can see that pretty well. You can see on the what time of the day, on what day that was happening. And the next slide, please. And on the same data, we can build different views on this, right? So you can put some of the relationships between the systems. We can easily put that on a graph instead and visualize it like this. So everything is based on the same data, different views for different tasks, and TimeSketch enables you to do that. Right. So we were able to very quickly spin up, horizontally scale this with a lot of workers using Aaron's system Turbinia, extract all the information that we need, put it in TimeSketch, and when we woke up, we were able to work on this collaboratively together, and we hopefully solved the case. And Aaron.
Yep. So kind of glossed over some of the details of some of the other tools that are kind of related to this. These are a couple of them. Plazo, some of you might know, is used for extracting timestamp information and creating the timeline that goes into TimeSketch. DF TimeWolf is another tool that we have that kind of glues some of these things together. In this case, we could use it to talk to cloud and clone disks and things like that. And then GR is like a remote live forensics tool that exists on the endpoint, so we can also extract information directly from live hosts. Yeah, so key takeaways here. Again, these are open source tools. You guys are welcome to and encouraged to use them. And if you guys have any feedback, please let us know. File bugs and pull requests are even better if you guys have things that you want to add. And yeah. So here's a few different links for the different tools that we have. The first one there, the Slack channel, is for open source forensics. And we have rooms there for most of these different tools. If you guys have your own open source forensics tools, you can create your own room there, and you're welcome to join us in that part of the community. And then yeah, here's different links for specifically for Turbinia and TimeSketch. And that is it.
And we're going to be here today and tomorrow, so if you want more information, details, please come talk to us. Thank you.
Thanks very much.